The first question asks us to consider the enthalpy diagram. So we have some labeling. First, our reactants are at the beginning of the curve, and the products are at the end of the curve. The energy absorbed by reactants is going to be from reactants to the top of the hill. We call this activation energy. This is the energy that we need in order to break reactant bonds. Once those reactant bonds are broken and we go to form products, this step releases energy. And so the amount of energy released by the products would be from the top of the hill down to products. So the net energy change, which is delta H, is going to be the difference between reactants and products. So the next question says, what is the delta H for this reaction? So the reactants have an enthalpy of 150 kilojoules, and the products have an enthalpy of 50 kilojoules. So then the difference between them is delta H, which is negative 100 kilojoules. So we can see that this reaction is going to release heat. The enthalpy is decreasing. So this reaction is going to be exothermic because the products have lower enthalpy than reactants, meaning that heat has to be released. So when we write delta H, we're going to include a negative sign to indicate that this is exothermic. The next question asks us to compare the stabilities of products and reactants. So high energy is less stable and low energy is more stable. So in this case, the reactants have high energy when compared to the products, which are lower energy. So this means that the products are more stable than the reactants. Next question has us doing some reaction stoichiometry. But this time we can use kilojoules in our conversion factors so we can make heat as a given or as a wanted. So the first question, what is the delta H of this reaction? It's going to be positive 67.8 kilojoules, meaning that this reaction is endothermic. Heat is a reactant, so heat must be absorbed for the reaction to occur. This reaction is endothermic, and the sign of delta H is positive. So what is the delta H if 1 mole of nitrogen dioxide is formed? So I'm going to start with 1 mole of nitrogen dioxide over 1. And I can always convert moles into kilojoules because my balanced chemical equation is in units of moles and kilojoules. So for every 2 moles of NO2, I'm going to absorb 67.8 kilojoules. So that means that my answer is 33.9 kilojoules. If 0.25, a quarter mole of nitrogen reacts, how much heat is absorbed? So again, we can convert between moles and kilojoules just using the reaction stoichiometry. And in my balanced chemical equation, for every 1 mole of nitrogen, I absorb 67.8 kilojoules. So when I solve, I get 16.95 kilojoules. The last question in this set asks how many grams of nitrogen are required to absorb 156 kilojoules of energy. So I'm going to start with 156 kilojoules, and I can always convert kilojoules into moles. And then I can convert moles into grams just using molar mass. So 1 mole of N2 goes along with 67.8 kilojoules. That's just from the balanced equation. And then the next thing to fill in is grams and moles. So that just means molar mass. So 1 mole of nitrogen is 28 grams. Notice that it's N2, so we have to double the molar mass of nitrogen. And when I solve, I get 64.4 grams of nitrogen. The next set of questions is about entropy. So entropy is a measure of disorder of a system. It has to do with how many possible arrangements exist for the particles within a system. So as far as states of matter, gases are going to have the most disorder, the highest entropy, because those particles are freely moving. There's many possible arrangements. And then solids are going to have the least disorder with liquids in between. So first, ice melts into a liquid. We're going from a solid to a liquid. So this means that the entropy is going to increase. B says that methane is deposited into a solid. So we're going from a gas into a solid. So that's going to be a decrease in entropy. Solid iodine sublimes into gas. So we're going from solid to gas. That's going to be an increase in entropy. And the last one, water condenses on a cold can. So we are going from liquid water to gaseous water to liquid water. So that means the entropy is going to decrease. Number 4, provide an example of a phase change that is endothermic and one that is exothermic. So endothermic are going to be phase changes where we have to add heat, so vaporization, melting. Exothermic is where we have to remove heat, so that's going to be things like condensation and freezing. For number 5, we're given a heating curve and we're asked to do some calculations here. So the heating curve that we're looking at was created by heating 10 grams of ice at negative 15 degrees Celsius all the way up to steam at 120 degrees Celsius. So for each segment of the graph, we're going to look at the potential and kinetic energy, and then we're going to calculate heat. We're going to calculate Q for each segment. So first, during the sloped segments, we can use Q equals mc delta T because we have a delta T. There's a temperature change going on during those portions. Note that the specific heat values are different for ice, liquid water, and steam. So we need to make sure we use the appropriate specific heat in our calculations. For the flat portions, so these are the portions where we do not have a temperature change. Instead, the added heat is being used to weaken intermolecular forces, and we get a phase change. So for those components, we're going to need to use either the heat of fusion or the heat of vaporization. And in this case, we're given those values in joules per gram. So if we multiplied by grams, we would get joules. So I'm going to start with the first segment, which is AB. Here, the temperature is changing. So if temperature is changing, kinetic energy is changing, and potential energy is not. So for this first segment, potential energy is constant, and the kinetic energy is increasing. The added heat is increasing the kinetic energy, the motion of the particles. So to calculate Q for this segment, we're going to use Q equals mc delta T. We said that the mass of water was 10 grams. We're going to use the specific heat of ice, and the temperature change here, we're going from negative 15 up to 0, so we're increasing by 15. So that gives me 315 joules for this component. To round for sig figs, we're going to need 2 sig figs, so 315 rounds to 320 with 2 sig figs. The next segment is segment BC, which is our first flat piece. So here, kinetic energy is not changing. Kinetic energy is constant because the potential energy is increasing as the heat breaks those attractions, those intermolecular forces, so that we can get our phase change. So because temperature is constant, kinetic energy is constant. In order to calculate Q, we're going to use the heat of fusion. So I'm just going to do dimensional analysis here. My heat of fusion is 334 joules per gram. So if I multiply that by my 10 grams, that gives me 3,340 joules. I'm going to need to round this to have 2 sig figs, so I get 3,300 joules for segment BC. The next segment is a pretty long segment. This is segment CD, and this is where we have finished melting all of the ice, and now we're in liquid water. So once again, the potential energy is constant because the temperature is changing. So the addition of heat is making those particles move faster. To calculate Q, again, because we have a delta T, we can use Q equals mc delta T. So the mass is still the same. We're going to use the specific heat for liquid water, which is 4.18 joules per gram degree Celsius. And the temperature is going from 0 all the way up to 100. So we have a delta T of positive 100. So I get 4,180 joules. This number needs to be rounded to have 2 sig figs, so I get 4,200 joules as my value for Q. Next segment is another flat segment, so this is segment DE. Here, once again, kinetic energy is constant because there's no temperature change, and the potential energy is increasing because we are adding heat to break those intermolecular forces. So this time, to calculate Q, we're going to use the heat of vaporization because we're boiling during this part. So my heat of vaporization is 2,260 joules per gram. I've got 10 grams of water here. So I get 22,600 joules. This again needs to be 2 sig figs. So that's going to give me 23,000 joules. Now we've finally reached the last segment here. So once again in segment EF, temperature is changing. So that means kinetic energy is increasing. As we add heat, those particles move faster, and potential energy is constant. So in order to calculate Q, I can use Q equals mc delta T. The mass is still 10 grams, but this time I want to use the specific heat for steam, which is 1.9 joules per gram degree Celsius. So here, my temperature is going from 100 up to 120. So my temperature change is positive 20. So when I solve, I get 380 joules. This needs to be 2 sig figs, and it already is as 380 joules. So we could total up what we got in each segment, and that would let us know how much energy does it take to go from 10 grams of ice at negative 15 to steam at 120 degrees Celsius. For question 6, we are going to use bond enthalpies to find the heat of reaction. So this reaction has Lewis structures. What we need to do is take count and take inventory here about which bonds are breaking and which bonds are forming. So I have a nitrogen to nitrogen triple bond that is breaking, and then I've got a couple of O2 double bonds that are breaking, and I'm going to form a nitrogen to oxygen double bond and nitrogen to oxygen single bond. So there is one nitrogen to nitrogen triple bond. I looked up the bond enthalpy from the enthalpy chart, and I'm going to multiply these together to get the total. Same thing here for O2. There's a 2 in front of my oxygen. So I've got 2 oxygen to oxygen double bonds that are breaking. So whenever I add these numbers together, this is going to be the endothermic change for bond breaking. So we're going to make that a positive number because we have to absorb energy to break bonds. On the other side of the arrow, we've got our products. So I've got a nitrogen to oxygen single bond. There's 2 of those, so I have to double the bond enthalpy. For the nitrogen to oxygen double bond, again, there's 2 of those, so I have to double the bond enthalpy. And when I add these numbers together, this is bond forming, and this is exothermic. So I'm going to put a negative sign in front of that. So by looking at the endothermic change and the exothermic change, we can see that the endothermic change is bigger. So that means that whenever I combine these two, I'm going to get a positive value for delta H. So that means that this reaction is endothermic, and we would put heat on the reactant side. Next, we're going to find the heat of the reaction, but this time we're going to use Hess's law. So Hess's law relies on taking equations and manipulating them until you get the equation that you want. So first thing I like to do is to go ahead and just rewrite my desired equation. This helps me catch how many moles of everything, what state of matter everything is in, just so it helps me with my canceling. So we'll start with reaction 1. And when I look at reaction 1, the thing that sticks out to me are the 2 moles of nitrogen monoxide. In my desired equation, nitrogen monoxide is a product, and in equation 1, it's also a product. So that tells me that I don't want to flip it. But in my given equation, I need 4 moles of NO, and in equation 1, I only have 2. So I can't get NO from equation 2 or equation 3. So the only way I'm going to get 4 is if I double this first equation. So I'm going to double the first equation, which means that I also need to double the delta H. So we've done everything we can with the first equation. Let's take a look at the second one. So the thing that stands out for me is the ammonia, the 2 moles of ammonia. In my desired equation, ammonia is a reactant, and in equation 2, it's a product. So that tells me that I'm going to want to flip this equation. I also notice that in equation 2, there's 2 moles of ammonia, and in my desired equation, there's 4. So not only do I need to flip this, I also need to double it. So I'm going to flip the equation and double it, which means I need to flip the delta H and double it. So I'm going to make negative 91 into positive and then double it. The last equation, equation 3, the thing that sticks out to me is the 2 H2Os. So I need 2 moles of water to be a product in my given equation. And in equation 3, that's exactly where water is. But I've got 6 moles of water in my desired equation and only 2 in equation 3. So I'm going to leave this one the same, but I'm going to triple it. So I'm not going to flip it, just going to triple it. So there it is tripled, which means I also need to triple the delta H. So now at this point, I've manipulated all of my equations. I just need to see what's going to cancel. So the 2 moles of nitrogen gas cancel because they're the same on both sides of the arrow. I also cancel out 6 moles of hydrogen, and that's it. So in my desired equation, I need 4 moles of ammonia. Okay, I've got that. I've got 2 moles of oxygen and then another 3 moles of oxygen, so that gives me 5, so that works. And then on the product side, I need 4 moles of NO, I got that, and 6 moles of H2O. So by combining and manipulating equations 1, 2, and 3, I get the desired equation, which means that I need to take the delta H's for all of those equations that I manipulated and total it up. So I get negative 1,628.2 kilojoules as my delta H. So number 8 is about heat flow. Draw arrows and explain the flow of heat for the 2 blocks. So heat flows from warm to cold. So that means that heat is going to flow from my 200 degrees Celsius block to my 100 degrees Celsius block. We're making some assumptions here that these blocks are isolated, that there's not going to be heat exchange anywhere else in the surroundings. So heat flows from warmer to colder. In this question, oxygen plus energy gives you an oxygen atom plus an oxygen atom. These bonds are being broken and energy is being absorbed. So bond breaking is endothermic, and we also can tell because energy is a reactant in this equation. There are lots of ways that we can find delta H. First, you could do an experiment to measure heat flow. So you could measure delta T and then solve using Q equals MC delta T. Remember that when pressure is constant, Q and delta H are the same thing. So for example, heat of neutralization lab, we mix 50 milliliters of 1 molar NaOH with 50 milliliters of 1 molar HCl. We get a delta T from the initial temperature and the final temperature, and we can use Q equals MCAT. Another way is to solve a problem. So this could be like a stoichiometry problem where you're given a chemical equation that includes heat. So find the amount of heat released when 10 grams of iron are formed. You could also see the solve for Q type. So how much heat is absorbed to warm 50 grams of water from 25 degrees Celsius to 100 degrees Celsius. We could also look at the heat that is absorbed or released during a phase change. So this would involve using the heat of vaporization or the heat of fusion. So something like how many grams of ice at 0 degrees could be melted by the addition of 400 kilojoules of heat. Then you also have specific heat type problems where we're trying to find the specific heat of something. So let's say that we have a 25 gram metal sample. It absorbs 100 joules of heat and it causes the temperature to change by 28.6 degrees Celsius. So there we could manipulate the Q equals MCAT equation to solve for C. The next type is Hess's law. So this is where we use the known delta H of two or more equations to find an unknown delta H. So we could take these three equations and manipulate them until we get the desired reaction, and then this allows us to find delta H. We could find it by bond enthalpies, so there we want to use the Lewis structures to determine which bonds are breaking and forming. Bond breaking is endothermic, so we apply a positive value, and bond forming is exothermic, so we apply a negative value. And when we combine the endothermic and exothermic enthalpy values, we get the overall change in enthalpy. We can also find delta H using an enthalpy diagram, so we can find the difference between reactants and products using the y-axis. If we see that the reactants are higher, then that means that the reaction is losing heat, so it's exothermic. If we see that the products are higher, then that reaction must absorb heat and is endothermic.